Okay, today we're going to cover section 5.5, which is about roots of real numbers, and then part of section 5.6, which is about radical expressions. So the first thing we want to talk about is simplifying radicals. So it says, to simplify radicals, you must know that the square root of a number and squaring a number are inverse operations, as are, taking the cube root of a number and cubing a number. Those are also inverse operations. So for example, let's say I had a cubed equals 125. Well, I know that 5 times 5 times 5 equals 125. So 5 would be the cube root of 125. So 5 is the cube root of 125. Just like, 2 squared is 4, so 2 is the square root of 4. So same thing holds with variables. So the definition of the nth root, so this is kind of a more general case. So for any real numbers a and b, if any positive integer, n, we'll say if a to the nth power equals b, then a is an nth root of b. So nth root, that could be, square root, cube root, could be the 4th root, 5th root. So this is just a general definition that encompasses all of the roots. So let's do a couple more examples. Since, let's say, 2 to the 5th is 32, well, 2 is the 5th root of 32 then. 2 is the 5th root of 32, since 2 to the 5th is 32. Similarly, 3 to the 3rd power is 27. So 3 is the 3rd root. Or we usually say, more commonly we'll say cube root of 27. Technically you could say it either way though. So, I'm sure you've all seen this radical symbol. This is a radical sign. So, there's always going to be some number here. If there's no number there, then that indicates the square root. But other than the square root, we always need to put a number there that indicates the nth root. So let's make a big radical sign here. And I'll just put the nth root of 20. Let's say that. So we're going to label the parts of our, so this is a radical sign. Just so when I refer to these things, you'll know what I'm talking about. The number under the radical sign is called the radicand. And then whatever n is here, we call that the index. So let's say we were taking the cube root, we would put a 3 there, and 3 would be our index. Okay, so we're going to start by simplifying some radicals here using our calculator. And these are going to be kind of perfect roots. So this is going to be a perfect cube. That's going to be a perfect 4th root. This will be a perfect square. So just getting comfortable with using your calculator. So clear everything out. And so to get this little index here, you're going to hit Control and then the little caret. That'll get the radical sign to come up, and it lets you type in an index. So we're doing the cube root of negative 27. So I'm going to put a 3 there. Do my right arrow, negative 27. That gives me negative 3. So that means negative 3 to the 3rd power would be negative 27. So this is negative 3. And let's try another one, the 4th root of 81. So again, I'm going to hit Control, caret. That's my, so I did Control, this one here. And I'm going to type in the 4th root. Oh, wait, I did something wrong. Hang on. Control, there we go. So the 4th root of 81. is 3. So that means 3 times 3 times 3 times 3 would be 81. So let's just add that to our notes. So we'll say, so negative 3 to the third power equals negative 27. And then this means, so 3 to the fourth power is 81. See how they're inverses of each other. Square root of 49 you probably already know. But just to be sure, we'll type it in the calculator. So hit Control. If it's just a square root, you can use this one. You don't need to type in an index. Again, if there's no index, it's assumed to be a square root. Square root of 49 is 7. So we'll put 7. And that means that 7 squared is 49. Okay, moving on from our calculator problems. We're going to talk about something called the product property of radicals. So this property says for any real numbers a and b, and any integer n that's bigger than 1, here's the property. So it's pretty easy to use. If I have the nth root of a product, like a times b, I'm allowed to break this up into 2 separate radicals, the nth root of a times the nth root of b. So I can break this product apart into 2 separate radicals, and as long as I keep my index the same. And we're going to be using that property in a minute here to simplify a root. So here are the 3 steps to simplifying a root. Step 1 is to factor into as many roots as possible. Roots as possible. So that means, like, factor in as many perfect squares or cubes, etc. So we'll say squares, cubes, etc. Okay, and next is we're going to use the product property to isolate the perfect squares or cubes or whatever root we're working with. So use the product property to isolate the perfect squares, cubes. Maybe it's something, we're working with a index of 4. It could be whatever number. Okay, and then lastly, simplify each radical. Okay, and those are our 3 steps. So write those down. When you're done, we're going to try some examples on the back. Okay, here we go. So example 2, we're going to simplify, and some of these will not be perfect squares or perfect cubes, so we can't just type them right into our calculator. We're going to have to use this product property. So I've got square root of 4x squared times y to the 4th. So most of you know 4 is a perfect square. So I'm going to go ahead and write it in terms of its perfect square. So again, my index, if you want to fill that in, if it's not written there, it's assumed to be a 2. So I'm going to rewrite 4 as 2 squared. Since I know the square root of something squared, those 2 things undo each other. So in the end, I'm just going to be left with the 2. X squared is already written as something squared. I want to try to now rewrite y to the 4th as something squared, so that that square root and the something squared are going to undo each other. So I have y to the 4th right now. And I know that if I square, or when I do a power to a power, I end up multiplying the exponent. So I want to think, okay, what times 2 gives me 4? Well, I know that 2 times 2 is 4. So if I write y to the 4th as y squared squared, that's the same as y to the 4th. And now I have it written as a perfect square. Now I'm going to use my product property to isolate each of these perfect squares. So this is the same as square root of 2 squared times the square root of x squared times the square root of y squared squared. I'm saying the word squared a lot. Okay, so the square root of 2 squared, these two things are inverses. They undo each other. So I'm just left with 2 there. Square root of x squared, again, inverses, I'm just left with the x. And then this square root and this outer, squared part here, those undo each other. So I'm just left with the inner part, which is y squared. And that would be simplified. Let's try another one. The cube root of negative 27c to the 6th. So if you don't know already, negative 27 is a perfect cube. We actually worked with that earlier. So I'm going to go ahead and, since my index is 3, I want to try to rewrite each of these parts as something cubed so that I can take things out of my radical and simplify it. Okay, because the cube root of something cubed, those two things undo each other. So I'm going to rewrite negative 27 as negative 3 cubed, because I know that's the cube root of negative 27. C to the 6th, I'm going to rewrite that as c squared cubed. Because I know that 2 times 3 is 6, so I didn't really change this value at all. And I wanted to get this written as something to the 3rd power. So that, oops, I forgot to do my index there. That's important. Put your 3 there. So that when I then use my product property and rewrite these, so I just wrote the first part. Now I'm going to separate. This is another cube root of c squared cubed. Now, okay, a cube root of something cubed, inverses, they undo each other. I'm just left with the negative 3. Cube root of c squared cubed, those two, and the cube root and this cubing here undo each other, so I'm just left with the c squared. And that would be my final answer. Simplified. Moving on, I have a 4th root. Okay, so I've got the 4th root of x to the 8th times y to the 12th. Now, again, I know that a power to a power, I multiply the exponents. And I want to try to rewrite both of these factors as something to the 4th power so that my index of, or my 4th root of something to the 4th power, those cancel each other out. So I'm going to rewrite x to the 8th. Well, I know 2 times 4 is 8, so I'm going to rewrite this as x squared to the 4th. I wanted to write it as something to the 4th power because it's a 4th root. And I know 2 times 4 is 8. So that's why I did that. Then I've got y to the 12th. Again, I want this to be y to something to the 4th, if possible. Well, I know 3 times 4 is 12, so I'll make it y cubed to the 4th. And then I'm going to isolate these. So I just isolated the 2 parts on the inside of the radical. And now I see, and actually if you want to skip this step, you do not need to show the step, but sometimes seeing this middle step helps people to simplify it. So 4th root of x squared to the 4th. These two things undo each other. I'm just left with x squared. And then I have the 4th root of y cubed to the 4th. These two things undo each other. I'm just left with y cubed. And that is simplified. Okay, moving on. I've got a square root of 72x cubed. Okay, so this is a bit different because 72 is not a perfect square. Nothing times itself is going to give me 72. So what I want to try to do is break this 72 down into 2 factors where one of the numbers is a perfect square. And I want to make that perfect square as big as possible. So you might play around and say, okay, let's see, 72 divided by, well, I know 4 is a perfect square, but is there anything bigger that goes into 72? Maybe, let's say, like I know 25 is a perfect square. Nope, that's not That doesn't go into 72. What about 36? 6 times 6 is 36. That's a perfect square. Oh, hey, look. 2 times 36 is 72. So I can rewrite 72 as, I'm just going to rewrite this as 36 times 2, because they're equal. And now I have at least a part of 72 is a perfect square. So it's still simplifying it. Now, x cubed, that's not a perfect square either. There's no exponent. I can't multiply anything by 2 to get 3. So what I'm going to do here is break apart x cubed. I'm going to make it x squared times x, because I know that I add my exponents to get 3 here. When I multiply two things with the same base, you add the exponents. This is like x to the first, so I didn't change the value anymore. And now I at least have part of my x's that are a perfect square. Okay, so now I'm going to isolate 36. I'm just going to write it as 6 squared, because that's what it is, times the square root of 2 times the square root of x squared times the square root of x. Okay, so I just broke each of those parts into their own radical using the product property. Okay, the square root of 6 squared, squaring something and taking the square root, inverses, so I'm just left with 6 there. Square root of 2, that is not a perfect square. There are no perfect squares that go into 2, so I'm just left with, that's sticking under the radical. The square root of x squared is just x, and the square root of x is, that can't be simplified anymore because it's not a perfect square. Now that kind of looks weird. Usually you want to put everything outside of the radical next to each other, so I'm going to say 6 times x. That's going to go on the outside. And then if I'm working with two things with the same index, I'm allowed to just multiply the two parts inside of the radical. So this is equal to 6x times the square root of 2x. So I just took those two parts of the radical and put them right next to each other. Okay, and that one is done. There's nothing else I can take out of the radical. Okay, we've got a couple more here. So next I have the cube root of 80 n to the 5th. Okay, so 80, if I check in my calculator, maybe I want to see if that's a perfect cube. Like if that's going to, just simplify. So I'll say control, the caret, and then 3, not plus, 3, cube root of 80. Okay, so I get a decimal. That tells me 80 is not a perfect cube. So what I want to do is try to think of a number that goes into 80 that is a perfect cube. So maybe like 2 cubed or 3 cubed. 3 cubed, 3 times 3 times 3 is 27. So check and see if 80 is divisible by 27. Nope, that gives me a fraction. 4 times 4 times 4, that's 64. That's another perfect cube. That does not go into 80. What about 2 times 2 times 2? That's 8. That's a perfect cube. 8 goes into 80. So I can use that. I'm going to rewrite 80 as 8 times 10, because I know 8 is a perfect cube. And then n to the 5th, okay, I want something to the 3rd power. 3 doesn't go into 5, so there's no way to really rewrite n to the 5th as something cubed. So I'm going to need to break up 5 into two different parts. I'm going to say, okay, n cubed, because that's a perfect cube, times n squared. Because 3 plus 2 would give me 5. I didn't change this value at all, and I at least have one part of it that's a perfect cube. I'm going to break this apart. Cube root of 8 times the cube root of 10 times the cube root of n cubed times the cube root of n squared. Cube root of 8 is 2, because 2 times 2 times 2 is 8. And you might even choose to rewrite 8 as 2 cubed, if that helps you see it better. 2 cubed. And then the cube root of 10, that cannot be simplified because no perfect cubes go into 10. Cube root of n cubed is n. Inverses, they undo each other. And there's no way to simplify the cube root of n squared. This is like the minimum power n has to be raised to simplify a cube root. Okay, and then again, everything outside the radicals we're going to put together. Square, or 2n, 2 times n. And then I can put these two parts back together. So the cube root of, this is 10 times n squared. That would be simplified. Okay, let's go through one more example. Actually, two. Sorry, I lied. Cube root of 54. Okay, test out and see. All right, is 54 a perfect cube? Let's see. Control caret cube root of 54. Nope, it's a decimal. So unfortunately, we got to think of something that goes into 54 that is a perfect cube. I know 27 is a perfect cube. I know 8 is a perfect cube. So let's start with the higher one, 27. See if that goes into it. Oh, it does. Look at that. And you could test out 8. Oh, that's a fraction anyway, so that didn't work. But 54 divided by 27. I can rewrite 54 as 27 times 2. The reason I did that, 27 is a perfect cube, and I'm trying to simplify this. Okay, x to the 16th. Well, 3 doesn't go into 16, so I can't write 16 as something times 3. But I can, like, go one lower. If this were x to the 15th, 15 is 3 times 5. So what I can do is say, all right, I'm going to write this as x to the 5th to the 3rd power. Again, I want to write something as rated as something to the 3rd power so that these two operations undo each other. So that gets me to x to the 15th, and then I've still got 1 left over because I want x to the 16th. So if I just multiply that by x, that'll be x to the 15th times x to the 1st. That's x to the 16th, which is what I started with. Y to the 4th, 3 does not go into 4, so there's no way to write 4 as something times 3. So I'm going to rewrite this as y cubed times y. Sorry, it's kind of crammed there. But because I want at least one perfect cube, then I've got 1 left over because it was y to the 4th. Okay, let's separate this into the cube root of 27 times the cube root of 2 times the cube root of x to the 5th cubed times the cube root of x. Oh, I'm running out of room again. Times the cube root of y cubed times the cube root of y. All I did was take all of these separate parts and write them under the cube root symbol. Okay, cube root of 27 is 3. This can't be simplified, so I'm just going to leave it for now. Cube root of x to the 5th cubed is just x to the 5th. Cube root of x is, that can't be simplified. It's got to be at least x cubed to simplify it. This leaves me with y. And then I've got the cube root of y, last but not least. And that looks weird. Let's put everything outside of the radical together. So 3x to the 5th times y times the cube root of, so everything that was under the radical was 2x and y. So that's 2xy under the radical. And that is simplified. Okay, lastly, we've got a special case here. So this is the square root of -4. And if you think about it, nothing times itself can give you -4. Because I would need, to get a negative number, like it's got to be a negative times a positive. So there's no two numbers that I can multiply together. Like -2 times -2, that's +4. 2 times 2, that's +4. So the rule is, this is technically a 2 here, even though it's not written. So since this is even, and this is negative, whenever your index is even and what you're trying, under the radicand is negative, you're always going to get no solution, or not a real number. Later we'll talk about imaginary numbers, so be excited for that. But for now we're just going to put that's not a real number. If you have an even index and a negative value under the radical, it's impossible. If you typed it on your calculator, it would say error or something like that. Okay, so that's your lesson. Here are your practice problems, so go ahead and get started on those.